Welcome back to the YouTube channel for everyone who either wants to learn the basics of single variable calculus or who has trouble falling asleep. Today we're starting a new chapter. This is called Functions and Continuity, and now we start studying maybe the main objects of this course, namely functions. And you might have expected to see them right from the beginning, because functions is usually what you do in school when you study calculus. You study derivatives and integrals, and we will do so in the following weeks. This will still take a while, but this is kind of the main object of studying calculus. And yeah, so far we've seen sequences and series, and it turns out that we will also need plenty of them in this chapter and the following chapters. So we are not getting rid of them. They are really always appearing basically throughout the course. But now we study functions and the term of continuity. You probably have seen the notion of continuity in high school, but maybe not, I think at least if you went into high school in Germany, you usually don't see the formal definition, but you just get a more intuitive picture, a heuristic way of defining this. Namely, you define a graph of, you define a function on the real numbers, and you define graphs, and function is continuous if you can just draw the graph without having to lift the pen and having to move the pen somewhere. So you can just draw it in one go. This is kind of the intuitive notion behind continuity, and this is also what we are going to formalize. And we are going to do this a bit more general for the complex numbers also, because the definitions are still the same. Again, if you're not familiar with, or if you're not feeling good with complex numbers, or if you still want some intuition about real numbers, just think of the real numbers everywhere. That's still completely fine. Okay, so we start with right off with the definition. First of all, let me say something about functions, because so far I've talked in general about maps, which are kind of maps between any possible sets, and some authors kind of use the word maps and functions synonymously. I personally don't like that. I'm a bit stricter with that, but I will just tell you what I will call a function here. Namely, we take some subset of C, which might of course also just be a subset of R, because R is in C. First of all, a real function on D is nothing but a map f from D to the real numbers. And now you can guess what I will write next. A complex function on D is a map f from D to the complex numbers. Usually, and later when we do the linear algebra, a function is something which kind of takes always values in the field. And here we are just studying the fields of R and C, as we've seen before. So this is enough for our purposes. But this is kind of what you should keep in mind. When you hear function, the values are then always in R or C. Okay, so this is just a function, so nothing spectacular. So just keep in mind, since R is a subset of C, any real function is a complex function, of course. Because we can see this still as taking values in C instead of R. Any real function is a complex function. Complex function. Okay, and now we come to one of the most important definitions from this whole lecture course. So it's a bit like I've told you when I introduced convergence that this is one of the most important things of this course. This will be kind of the second in this row, so of this most important definitions, because everything that's coming is based on this. And it looks similar to convergence, but a bit more complicated, but I hope I will be able to provide you with some intuition. Okay, first of all, we have a function. So we have a subset D, which should be the domain of our function. And now we take one particular point, A and D. Now we say a complex function f from D to the complex numbers is called continuous in A if the following holds. Remember, we had convergence of a sequence was for all epsilon bigger than 0, we have an n0 in n such that blah, blah, blah. And for continuity, it's similar, because we also start in the same way. We say the following: for all epsilon bigger than 0, there exists a delta bigger than 0. So instead of an n0, we have now a delta, such that the following holds. The value of f of x minus f of a, so for x is then supposed to be close to a, and we want that the value, the difference of these values, is smaller than epsilon whenever x is sufficiently close to a, namely for all x in D with x minus a to the absolute value smaller than delta. So for any small number, we can find another small number such that another small number delta, so that if x is delta close to the point A, the values of f at the value of f at x is also very close to the value of a. Just a different number here, but keep in mind epsilon should be very, very small, and we can still find some delta which has this property. So we kind of know that near a become arbitrarily small, the values of f become arbitrarily small, arbitrarily close to the value of f at a. Okay, and to illustrate this, let me kind of do a little drawing. I prepared something on the other board. Okay. Okay, let me just check on my screen. Yeah, should be readable. Okay. So first of all, the real case. Imagine we have a function from R to R, and you can hopefully recall from high school that you can draw the graph of this function as some subset of R2. Namely, on this x-axis, we draw the point at which we evaluate. So this would be then the value of x, and on the y-axis here, we would have f of x, so the value of the function. So at the point A, we would have the value f of a. Okay, and this is just some function which, I won't make precise or anything, but this is continuous. The idea is kind of the graph. You can draw this in one go. But as I said, this is of course not a formal definition. So what now does this definition say? Maybe I can, yes, okay, it's still invisible on the camera, okay. So here's the definition. For all of these epsilon, we can find a delta such that, okay, for this I will need some colored chalk, so just to make it visible a little better. Okay, first of all, we have some epsilon. So we consider first of all which are the values of a function which are, so we want to demand that the values of the function are epsilon close to this. And so epsilon close to f of a. And epsilon close just means the difference of the value and f of a is smaller than epsilon. So what is this as a set here on this axis? So if I say how can the values be such different as small? This actually means that we have some value here and such that this is f of a plus epsilon, and this here is f of a minus epsilon. And the set of points on this axis, which are kind of epsilon close to f of a, is precisely this interval here, if we just view this as a line and not as a vertical something. So we want that the values of the function are in between these two for some sufficiently small delta. And let me just draw some lines here that help us see what's going on. Okay, so we want the values between these two horizontal blue lines. So this is the point alpha, and so we need some delta neighborhood of alpha such that the values of f are within this blue corridor. And here we can see that this delta is easy to see. For example, we see that as long as we're kind of between here and here, we always stay within this blue range. So this means we can just draw some delta, and we also need to take some points which are until a plus delta here and a minus delta here. So everything in between there in this corridor. So let's, for example, take something like this here, and on the other side, this would be then, so to make it symmetric here, this. So this would be a plus delta, this would be a minus delta, and let me now draw some some vertical lines here to help us see what's going on. Whoops. Okay, how does this look? Okay, not too good, but anyway. So we see that the part of the graph of f, which is, so the values of f over this interval here, if we just restrict to this interval, then this is basically this part here of this of the graph. Let me take a third color. So this part of the graph, and we can see kind of which values does f take on this part, and we see that this is kind of this piece of the graph is contained in this blue corridor. So the values are of course in this small range here, which is kind of part of this blue strip. And so of this corridor here. So this means the values are close enough. So for this epsilon, we have found some delta. Okay, if we now would do something different and would take a smaller epsilon, let's say we okay, this is something, I hope this is still visible on the video. This is now a very small epsilon. So we would take this purple horizontal lines. This would then be f of alpha plus epsilon prime, let's call it like this. And here we would take f of a minus epsilon prime, and we would take some strip like this. I hope it's still visible. I'm not sure about the camera quality. Sorry about that. I'm now in this room again with a not so good camera. So here we can see we need to stay within this purple strip. We can still find the delta, but we need it smaller than this one, because here we see that kind of at the end of this interval here, we are kind of leaving this this purple strip, and the same here. So we just need to find a smaller delta. But if we would take something sufficiently small, let's say we'd have like here. So here this would be a plus delta prime for some number delta prime that we take, and on the other side we take the same thing here. Oh, sorry, this would be a minus delta prime. So at this point we can see that everything which is kind of between here and there of the graph stays in the purple strip. So again, for this epsilon prime, we can find a delta prime with a nice property, and so on. And we could take epsilon prime smaller and smaller and smaller. We would have to take a smaller delta, of course, and we would have to shrink that one as well, but we could always find one. That's the important part here. Okay, yeah, I hope it's still visible on the video later on. Can't make any promises here. Okay, so now, same situation, but now for complex numbers. I have continuity of a complex map, and of course here I can't draw a graph anymore, because this is something which is kind of a two-dimensional plane, and this is a two-dimensional plane, so the graph would be a subset of a four-dimensional space, which I obviously can't draw here. But what you can do is kind of draw this separately. Let's say this is the domain here. This is a copy of C, the whole plane. And this should be the codomain, so the values here. And F is considered as a map from here to there. And we assume that, so we want F to be continuous. And we say that this is a point A, and this point is mapped to some other point F of A here. So now we also need to consider, again, the same definition. It's still in there. So for all epsilon bigger than 0, so first of all, we think about this condition. So we want the values to be epsilon close to f of a. And if we think about this geometrically, I will make this more precise later in this lecture, in the next lecture, I think. Anyway, but here we know that the values have to be epsilon close to f of a. And now the set of points which are kind of epsilon close, or whose difference to f of a is smaller than epsilon. This time it's not an interval as it was on this left-hand example, but here it's a circle, because we get here, this is not a circle, I'm sorry about that. I'm terrible at drawing a circle, freehand. Okay, so this is a very bad circle, sorry about that. But the circle should have radius epsilon. This is the set of all points whose kind of, such that the absolute value of the point minus f of a is smaller than epsilon. So the interior of this, so-called circle. So this won't be a circle. Now what does the definition say in this case? Now it says that we find some delta neighborhood, as we will later call this, of the point A, which is completely mapped into this part which is epsilon close. So this means this, to describe these points here, the points x such that x minus a to the absolute value is smaller than delta, this would again be a circle, but this time a circle around a. Let's draw it and take a different color here. So say like this. So this radius here, this is delta. Whoops, sorry, hope it's readable. So this is a circle of radius delta, and the condition now says that the images of this circle are such that this condition holds, which means that it's part of this circle here. So this means the image of this thing, this might look completely strange and might be a very complicated set, but it is contained in this set. This means it could be, I don't know, something like this. But we only know that it's contained in this big white circle. So this thing here, this would be f of, so if we call this circle here B, this would be f of B, this pink set. Okay, so we can find such a such a circle. And again, if we can now shrink and shrink and shrink epsilon, and at some point, of course, we cannot take this b anymore because we've shrunk the circle so much that this is not part of the circle anymore. So, but then still we might kind of reduce the circle to a smaller radius, and then still we can find some smaller circle which we can map into the other circle like this. This is what continuity does. So this is why this expresses the this notion of something that's the values of the function. So if points are small, are very close to each other, then the values are close to each other. That's kind of the way of formalizing this. Okay, this is the idea behind continuity. And a third part of this definition, so we said this is continuity in a point A, and more generally we call a function just continuous if it's continuous in every point. So f from D to C is continuous if it is continuous in A for all A in the domain. This is what we call a continuous function. Okay, so this was just some heuristics, kind of fancy image, but I want to give you more formal examples. So we just consider some examples where we can really use this definition and check this. So example 3.2. I give you a trivial one, a simple one, and a complicated one. Okay, first of all, the trivial one. We take some value c in C, some fixed number. Then the function which goes from C to C, which just maps everything to C, so the constant function, is continuous. Okay, this is really not very exciting, but this is easy to see. I'll be so smug as to call it trivial, since we know that f of x minus f of y, if this absolute value which we need to investigate in the condition of continuity, if f is constant, this is of course always 0, because these two values are the same. Okay, so this is smaller than every epsilon we can imagine for all kinds of values of x and y. So yeah, there's nothing to show. So this is smaller than epsilon for all x, y in C, epsilon bigger than 0. So for each epsilon, we could choose delta as big as we want. This is still always satisfied. Okay, this was the trivial example. Now a simple example. So if we this was the function we considered. Second example, a bit more exciting, but not that much. F of z is equal to z. Okay, also not very exciting, but still, I want to discuss that this is continuous. And this is also visible straight from the definition. Namely, we take a point A and C and want to show that it's continuous at A. And we need some epsilon bigger than 0, so some arbitrary number, and we need to find a delta which satisfies this property with respect to this choice of epsilon. And here this is almost trivial, because with delta equal to epsilon, it follows for all x in C with x minus a smaller than delta, so that this absolute value is smaller than delta. So in this setting we need to show that f of z minus f of a to the absolute value is smaller than epsilon, but now this is trivial because f of z is just the identity, so this just keeps every point. So this is the same as z minus a to the absolute value. Sorry, I wanted to call this x and not z. Oh no, I've called it z. Sorry, then just to keep it unique, I will also call this z here. Sorry. This is the same as z minus a because f is just defined that way. This is by assumption smaller than delta, but delta is equal to epsilon. So we've shown, although it's very simple arguably, that for all z with this property, it follows that f of z minus f of a to the absolute value is smaller than epsilon, if we just follow this guideline here. Okay, so this shows that f is continuous in A. So f is continuous in A. Okay, third example. For this I need, maybe I'll start here. Okay, we take f from C to C, and now slightly more interesting, f of z is z squared. Okay, this is a non-trivial example, and so this is now something which is really not that easy to see how to show that something is continuous, and I will show you how to do it in this for this concrete function. Again, we have some point A and C, and we want to show that this is continuous in A. First of all, we do a nice little computational trick, namely by the triangle inequality. It follows for all x and c that we can just write this point. We'll, so far, it's absolutely not obvious what we do this for, but I will see in a bit. This is the same as x minus a plus 2a, okay, which is the same, which is smaller than or equal to, by the triangle inequality, x minus a to the absolute value plus 2 times the absolute value of a for all x and c. Okay, why we do this we will see later, but this is some trick that we will need in a tiny bit. Now we can do namely the following estimate. We want f of x minus f of a. This is something we want to make small, and so we do some computation before, and then we can see, kind of given epsilon, how we have to choose our delta. So this is by definition the same as the absolute value of x squared minus a squared. Now we use the third binomial formula, as we call it in German. So this is the same as x plus a times x minus a. So this is the same as x plus a to the absolute value times x minus a to the absolute value. Okay, there's nothing fancy has happened. Now we use this estimate here. So this now says, so if we call this inequality here star, we use this at this point and get that this is smaller than or equal to x minus a to the absolute value squared plus 2 times the absolute value of a times x minus a to the absolute value. Okay, we've now reformulated this a bit. This advantage, this has now the advantage that only x minus a to the absolute value is contained in there, and no squares inside this value anymore, because this is the part that we can kind of make small by choosing delta efficiently. So, given this computation, we can now show the continuity. Namely, if we have some epsilon bigger than 0 given, some number epsilon bigger than 0, so we need to find some delta such that this thing here becomes smaller than delta, and by this computation, smaller than epsilon, sorry, if this difference here is smaller than delta, and by this computation here it suffices to show that this here is smaller than epsilon if delta is small enough. And this is what we are going to do now. And then we now choose delta to be the following, the minimum of 1 and epsilon over 2 absolute value of a plus 1. This is again a proof which is kind of done by reverse engineering, because now at this point it's not really obvious why delta should be chosen in this way. But this kind of afterwards you see that this delta really makes it work. And this we will do now. So if we have this, then for all x and c, such that the difference to a is smaller than delta, so x minus a to the absolute value is smaller than delta, we get the following. We get that, so f of x minus f of a. So this is smaller than or equal to, let's do this again, x minus a squared plus 2 absolute value of a times x minus a to the absolute value. Okay, now we see, by definition, delta is at most 1. So it's the minimum. If this is bigger than 1, we just put that this is 1. If this is smaller than 1, we take this value. But anyway, this is always smaller than 1. So this means that the square of this thing, because this is smaller than delta, the square of this thing is smaller than or equal to just this thing itself without the square. Squaring of a number which is smaller than 1, of a negative, of a non-negative number smaller than 1, squaring it makes the number smaller. So this means that this is smaller than, since delta is at most 1, x minus a to the absolute value plus 2 to the absolute value of a times x minus a. So this is now the same as 2 times the absolute value of a plus 1 times x minus a to the absolute value. And yeah, this is smaller than delta. So this is smaller than 2 absolute value of a plus 1 times delta. And now, since delta is also by definition smaller than this guy here, we know so that this here is, so since delta is smaller than or equal to epsilon divided by 2a plus 1, and if we just put this in there, and we see that this kind of multiplies out the denominator, so this is smaller than or equal to epsilon. So this shows by just following these inequalities, since they also go in one direction, so it's really a nice chain of inequalities. We get that f of x minus f of a to the absolute value is smaller than epsilon for all x in C with x minus a to the absolute value is smaller than delta. And this shows that f is continuous in A. So f is continuous in A. Okay, so this was a more complicated example. And as you can see here, this was not that easy. So in general, it's kind of really non-obvious if you have given an epsilon bigger than 0, how to find a suitable delta. This was not that very complicated as a function. We just take that z squared. There are way more complicated functions than this. And so you might imagine in general, it's very hard to kind of prove something with this epsilon delta definition by hand. So to show really something is continuous. For this purpose, there's a theorem that we shall discuss next. And we can also give another definition, or reformulate this definition of continuity and use sequences instead, and convergence of sequences, which is often more easy to handle, as we shall see in the rest of the section. But this is the way you can kind of get rid of this epsilon delta criterion, and this we shall see next after I have erased the board. Sorry for the sudden change of rooms. I had to leave the lecture hall because there was another course in this lecture hall scheduled, which I didn't realize until it was that way. But I could organize a camera, so I'm going on in this room, which is probably even nicer for you because it's nicer to read and to see via this camera. Okay, this was the definition of continuity. I'll just leave this here as a kind of reminder if you have to look it up what continuity means. And as I've promised you, we now reformulate continuity via sequences. This is theorem C3, and this criterion for continuity is sometimes also called sequential continuity. Okay, namely, we have again a domain in C, we have f from D to C a function, and we have a point A and D to which we want to, with respect to which we want to formulate continuity. Then f is continuous in A, is continuous in A if and only if the following sequence criterion holds. For each sequence in D, each sequence xn in D which converges to A, so with limit n to infinity xn equal to A, it holds that the values of the sequence, of f at this sequence, also converge against the value of f at A. So for each of these sequences, it holds that the limit of n to infinity of f of xn is equal to f of A. So whenever they converge against the point in the domain, the values converge as well. And this this is very easy to see intuitively. So if we have a point A, if we have some continuous function here in the real numbers, and so this is the real situation here. So if now we have some sequence of points which kind of converges here to this value A. So here's the point here. Here we have f of A. If we have some sequence, let's say we come from this side, and these are now these dots here now indicate the sequence. So we have x1, x2, and so on. And we would then approximate A from the side and converge closer and closer to A, then of course the points on the graph here would be this and this and this and this and this. And of course here we can see if we go closer and closer to this here, the values of these points at the graph, this would be then over here. So of course now I can't see much anymore, but here these would converge to this value as well. So if we approximate this point here, we approximate the value. And this kind of means there's no unexpected jumps or anything. There's no gaps in the function. We will see a counterexample in a second after we've proven this theorem. So this is sometimes a nicer way because we can handle sequences quite well. We know a lot about sequences. Of course, this says for each sequence. So again, we have to argue abstractly and just cannot just take some random sequences that we like. But this is indeed very helpful. This can help us really to find out some notions about continuity that we will see afterwards, or some applications of this criterion, which are really useful and which show that these epsilon delta criterion, in most cases you don't need it when you want to compute some continuity, really explicitly compute something. Okay, how to prove this? So, okay, we do first this direction here. So we assume continuity. I want to show the sequence property. Again, I've written down this definition of continuity here. So for each epsilon, we have a delta such that the values of f are, the difference of the values of f is smaller than epsilon as soon as the points are delta close to each other. So what does this help us? So we need to start with some arbitrary sequence, of course. Let xn be a sequence in D with limit of the xn equal to a. So we have such a sequence, and we have to show that the values then converge as well. So what do we need to show? So we have some epsilon delta thing, but for convergence, the definition of convergence also involves epsilon. Namely, for convergence, we need to show, and this is just a rephrasal of the definition of convergence. For each epsilon bigger than 0, there exists an n0 in n, such that the following holds, such that f of xn minus f of a, so we want to show that this sequence converges against that value, that this is smaller than epsilon for all n bigger than or equal to n0. Okay, so this we need to show. So we start with some random arbitrary epsilon. Since f is continuous, we have a delta, so there exists a delta bigger than 0, such that, let me write this again, such that if, just formulated in a slightly different, more concise way, if this holds, if x is delta close to a, then it follows that f of x minus a to the absolute value is smaller than epsilon. Okay, this is what we have. So, but we know that since this sequence xn converges to a, and we know this, so since limit to infinity xn is equal to a, we particularly know that this here holds for almost all n in n, so that xn minus a is smaller than some given delta, so this delta is something that we have now, and we can kind of be smaller than this delta, which means since this is the case, there exists an n, let's call it n1 in n, not to confuse it with this one, such that xn minus a is smaller than delta for all n bigger than or equal to n1. But this means, by this criterion here, that f of xn minus f of a is smaller than epsilon for all n bigger than or equal to n1. And this is what I wanted to show by this. Now it's now n1 instead of n0, but this is a number that we need here. So this really shows that the limit n to infinity of f of xn is f of a. And this is what we needed. Sorry, this is only one direction. Sorry. This completes the proof of this direction from here to there. Okay, now for the other way around. So we need to conclude from this sequence criterion that we have continuity. And this might be sound a bit more challenging. And it's an interesting argument, namely we go by contradiction. Assume this condition holds, but f was not continuous in A. What then? What is the negation of continuity? So we want to say this condition is not satisfied. This says that for all epsilon, this and this holds. So the negation first says that there exists some particular epsilon for which this does not hold. This is the negation of this condition. Which means there exists some particular epsilon, which I call epsilon 0, just to make clear this is some particular. So there's an epsilon bigger than 0 such that this is not satisfied. And this means for this epsilon 0, we cannot find a delta such that this holds. And this means that for each delta, there's something which contradicts this inequality. And this means there exists an epsilon bigger than epsilon 0 bigger than 0 such that for all delta bigger than 0, there exists an x in D with x minus a smaller than delta, but such that the difference of the values of f is too big, namely that f of x minus f of a to the absolute value is bigger than or equal to epsilon 0. This is the negation of continuity. This is more about logic and quantas and so on. So yeah, really the contraposition to this is, the negation of this statement there above. So I hope this is somewhere understandable. So we have some epsilon 0 such that this condition is violated, and violated means for all epsilon delta bigger than 0 we can find some bad guy which damages this condition that we actually want to have continuity. Okay, but this means in particular, so we have this epsilon 0 and we know that for all delta bigger than 0 we can find such an x. So this particularly means for all n and n we can find an xn in D with xn minus a to the absolute value is smaller than 1 over n. So this time we take delta to be 1 over n, such that this holds, but such that f of xn minus f of a is bigger than or equal to epsilon 0. Okay, so we can find this for every n. What we now do is really consider the sequence. Then if we take the sequence xn, n and n, okay, if we see this condition here, this easily implies that xn indeed converges to a if we consider such a sequence. So then this converges to a. So by assumption, we must have that the values, the limit of the f of xn, that this converges to f of a. But since we have this strange condition, we can get a contradiction. Namely, so what we would need for continuity would be that to this first condition to hold is that this sequence here. So if f of xn would converge to f of a, this here would converge to 0. But this is not the case, since we know that each of these values here is epsilon 0 or bigger, and this is a positive number. So this is bounded from below by a positive number, and so it cannot converge to 0. Right? So if it must not converge, but we know if it converges, but if it converges, the limit is also bigger than or equal to epsilon 0. So this just cannot be the case at this point. So this does not converge to 0. And this implies, as I just said, that the sequence f of xn does not converge to f of a, and this is a contradiction, since this violates the assumption that we have made. So this contradicts the assumption, and so f is not, it follows that f is continuous in A. Oops, in A. Okay, so this is a nice criterion for continuity, and with this criterion I will show you that some simple function is not continuous, which is an easy example, but I will just show you how this follows. We consider the function from R to R, where f of x is, and we define it case-wise, it's either 1 if x is bigger than or equal to 0, or 0 if x is smaller than 0. So this function is called the Heaviside function. Okay, the graph is very simple. If this is the real numbers, we just have, here we have everything equal to 1, and yeah, here it's 0. Maybe just make this a bit thick to indicate this. So here it's 0, and at this point excluded. This is something that we note by making a circle that we, if we say that kind of will go to 0, but if 0 is not included anymore, you can just draw a circle here, which shows that this is not included, but that indeed at 0 we are at this point here. So this obviously has a jump, right? And this should then violate the continuity property from this intuition that we want to provide with this. By the way, the name Heaviside function, you might think that this is called Heaviside because this function has a heavy side. So everything right off the graph is kind of heavier. Or this is not the case. Indeed, this was invented by a guy named Oliver Heaviside. I'm not kidding. This is really the case. He was a mathematician and physicist. So it's really named after a particular person. Okay, and here, okay, the problem is of course that f is not continuous in 0. And this follows immediately from this sequence criterion. Namely, if we take any real sequence, with xn negative for all n in n, and such that the sequence itself converges to 0. For example, we could just take xn to be minus 1 over n. Then the limit of n to infinity of f of xn, this is a negative number, so the value is always 0. This is the limit n to infinity of the constant sequence 0, which is of course 0, but this is not equal to 1, which is f of 0. And so by the previous theorem, the condition about the sequences is violated, and so we get that this is not continuous. So it follows that from Theorem 3.3, f is not continuous. Okay, very simple example. So we can now use this sequence criterion, this condition, to derive some nice properties of continuous function that are useful for computing with them, and I will just erase the board and tell you about them. We now want to discuss that continuity behaves well with respect to the algebraic operations we are using all the time. And this basically is now a consequence of the fact that convergence behaves well with respect to addition, multiplication, and so on, as we have discussed for sequences. Okay, and I will basically summarize them in one big theorem and just prove one part of it, because the others are really proven the same way. So we have a domain D subset of C, we have some point A and D, and we have two functions this time from D to C, and they are both supposed to be continuous in the point A. Both continuous in A. Then the following functions are also continuous in A, namely the first one, and I also introduced this notation in this theorem, which I will use frequently from now on. I take f plus g from D to C, and of course the definition is very simple. The function f plus g at x is defined as f of x plus g of x, so just addition of the values of the functions. This is again continuous in A. Okay, and in the very same way, the product of functions is defined. So f times g from D to C, f times g at x is defined as f of x times g of x. This is continuous in A. Then if f of x is non-vanishing for all x in D, then we can define 1 over f from D to C, simply by saying 1 over f at the point x is defined as 1 divided by f of x. So just division in C, and we just take this notation here as for functions. This is continuous in A. And finally, the function real part of f and imaginary part of f. So these are two functions which are going both from D to R, where, and now you can tell what I can guess what it is. So the real part of f at x is of course simply the real part of the value f of x. So just at each point we take the real part of the function at this point. And the same for imf. So imf of x is defined as the imaginary part of f of x. Sorry, squeezed it a bit. These are continuous in A as well. In A. Yes, so this is the theorem here, and this is basically, looks very similar to what we've done for sequences, and this is why this all works, because we can apply the respective result for sequences here. So I will prove part A in detail. So we take a sequence, be a sequence in D, which converges to A, and all we need to show is that this automatically then f plus g, the values of f plus g at xn converge to f plus g of A. And this is basically just bookkeeping at this point. So we take a sequence which converges to A. Then by the theorem I had before, so by the sequential continuity, by theorems 3, and what we now need is that limits behave well with respect to sums. This is what we've seen quite a while ago. That was theorem 2.7 part A. Namely, then we get that the limit n to infinity of f plus g at xn. So by no parentheses, sorry. By definition, this is just the same as the limit n to infinity of f of xn plus g of xn. And now this is where theorem 2.7 kicks in. So this is the same as the sum of the two limits. This is the limit of n to infinity, because we know since f and g are continuous, this converges and this converges. This is theorem 3.3. So these are convergent, so this is why we can apply this theorem 2.7. This is the only important thing that we need to know. So these two already converge. This is what we know. This is the same as limit of f of xn plus the limit of g of xn. And since f and g are continuous, this is just f of a plus g of a. And this is just writing this in for our fancy function, f plus g of a. This is what we needed to show. So it's basically just really one big computation with limits. So everything that's behind this here is properties of convergence, right? So there's nothing too complicated coming in there. So, and the other parts are proven analogously. So for B, we have the same for products. We have seen that if a product of sequences converges, then if the sequences converge, then their product converges against the product of the limits. And this is the same way, just replace every plus by a dot, basically, here in this computation. So this is using theorem 212b. Oops, you're messing up my notation, sorry. We need that f and g are continuous. Yep. Here goes the structure, I'm sorry. Okay. So we just need to take the respective theorem, and for C we've already seen that if a sequence is non element of the sequence is 0, then the sequence of its inverses also converges against the inverse. So this is also shown in the same way using theorem 214 in this case. And for part D, we've seen that convergence of a complex sequence is the same as convergence of the real part and the imaginary part. So this was theorem 220. And so we show these properties. Okay, so this already gives us a lot of leverage, because we have if we know that some functions are continuous, basically everything we can produce from these functions with plus and multiplication, so additional multiplication and also taking inverses here, everything will still be continuous. So this already gives us a lot of possibilities. So just one elementary consequence of this, namely one of our favorite classes of functions is now continuous. So corollary 3.6, namely every complex polynomial. This is what I haven't formally defined yet, and I will do this right now. Polynomial, i.e. Every function f from C to C of the form f of x is a sum from 0 to n, a k x to the power of k. So this is what we call a polynomial. So where n in n, and where the coefficients here are just complex numbers. So the numbers a0, a1, an in C are just complex numbers. So every function of this type is continuous. And this, there's nothing to show basically, because we just need parts A and B of the previous theorem. And the examples we've seen. And we've seen that f of x is x, this is continuous, and that constant functions are continuous. And if you take a look at the polynomial, this is basically just produced by first taking powers of x, which is just the product of f of x is x with itself, multiple times maybe, but then we can just apply this result again and again and again. And the same here, we have here constant functions, so constant functions are continuous, and this is just multiplying these x to the k with constant functions. It's not doing anymore. So we're just taking the functions we have from the example and doing all kinds of things we can do with plus and multiplication. So yeah, this is what we get from this. So this was example 3, 1, 1, and 2. Okay, and this is all we need. So we just need to apply this theorem again and again. So if this holds for the sum of two functions, this also holds for any finite sum of functions, because we can just add the first two and get continuity, then we can add the third one and still get continuity, and add the fourth one, get continuity, and so on and so on and so on. And this is what we're doing precisely to achieve this. So polynomials will also be important later on, so we will of course discuss them. And I mean, all of you should have seen polynomials in high school and discussed them a bit, and we will treat them further later on. Okay, there's one more property of of continuity, which still gives us much more leverage. Namely, we haven't talked so far about the composition of functions. So far we've just multiplied and added them and so on, but we haven't taken compositions. And this is what we need to do in here, or what we want to do next. Namely, we take two domains, D1, D2 in C. Then we take a function f, which goes from D1 to D2, so a complex function whose values completely lie in D2. And we take a second complex function, D2, from D2 to C. So this means this goes from here to there, and then we pick it up with G, so we can just take the composition of these two. And yeah, we need a point, A in D1. And now how is this continuity rule now? If f is continuous in A, and if G is continuous, but it makes no sense to say that G is continuous in A, because we are in D2 and A lives in D1. But what we need here is that G is continuous in the point f of A. This is a point in D2, right? So this is what we need. If this is continuous in this point and that point, then the composition, which is now G circ f, this here. So we first take f and then take G. This is denoted in this way. It's always a bit confusing at the beginning, I must admit. But this is kind of the way it makes sense. So the composition here that we've seen, I mean, this is what you already introduced. This is continuous in A. Okay, and this is also, looks more complicated than it is because the proof of this is actually very simple. Namely, again, we can take sequences. Okay, let, again, xn be a sequence in D1, which converges to A. And so we need to show that the composition G circle F at xn, that this sequence then converges to G circle F of A, which converges to A. So, first of all, we know that since F is continuous, we get from Theorem 3.3, so Theorem 3.3, that F of xn then converges to F of A. So G continues in A, sorry. We get this. Okay, but now we have a sequence which converges against F of A, and now we can use that G is continuous in F of A, because if there's any sequence converging to F of A, we know that, again from Theorem 3.3, that the values of G at this sequence then converge to the value of G at the limit. So this means that since G is continuous in F of A, we can again apply Theorem 3.3 and get that the limit n to infinity of G of F of xn as G of F of A, just by continuity. But if we just take a look at what stands here, this is equivalent to just saying the limit. And this is the definition of the composition, so this is G circle F at xn, and this then goes to G circle F at A. And this is what we wanted to show. So this implies, again, by this implies, again, by Theorem 3.3, since we've taken an arbitrary sequence in the beginning, that G circle F is continuous in A. Okay, and this gives us now a lot more leverage, as we will see later on. So we will definitely see examples of that, but this is, another important consequence. Okay, now I'm going to erase the board, and then I'll present you a different concept of continuity, which is a bit stricter, but sometimes easier to handle, as we shall see next.